the density contrast or the thickness at that depth. All right, so all we're doing here is changing, or not the thickness, but the radius of the sphere. Obviously, as we move the sphere deeper, the gravity anomaly becomes less because r squared becomes less, but it also becomes smoother. It affects more and more of the measurement locations. So this is as if we recorded a gravity survey at the surface. What's the horizontal axis here? It's x. So we've measured gravity continuously along that surface to get that profile. Okay, the gravity anomaly of a buried infinite slab. I'm not going to go into the details of that, but notice that the slab, what's really interesting about the slab that you can see? Does it matter at what depth I put the slab? No. I can put the slab at any depth, and I'm going to get the same result. Now that's scary, right? I mean, I'm giving you a lot of frightening examples of gravity inversion. In reality, again, we kind of look for signatures of the gravity data, and then we interpret them in terms of relatively simple bodies with our understanding of geology. That's really how we measure or we analyze gravity data. So this curve right here would be an example of a truncated slab. It wouldn't go constantly all the way across. There'd be less density as we got to the edge of the slab. And we can approximately, if we had a really simple example like this, we can approximately estimate, if we have a maximum at 5, and we think the edge of the slab is at 0, the gravity anomaly at that point will be 1/2 times 41.9 times delta rho delta h. Again, notice that this interplay between the density contrast and the thickness. All we can measure is the product of the thickness and the density contrast. We're going to have to either put some constraints on the density contrast and then basically measure the thickness, or we're going to have to put some constraints on the thickness and measure the density contrast. So it really depends on what you're looking for here. If you're looking for, if you know, for example, that there's an ore body of density contrast 1.5, and you want to know how thick it is to determine whether you're going to mine it, okay, then you constrain the density contrast and measure the thickness. On the other hand, if you're looking for a certain lithology, and you know that there's a fault that's cutting this particular thing, maybe and you know the thickness of it, maybe you, or the density contrast, maybe you're trying to understand the thickness. And this is the general equation of that curve up there. Okay, again, the thing we don't know is both density contrast and thickness. Okay, so the same issue occurs as with the infinite slab, although not quite as badly. You can see that as we put this slab deeper, we've got a smoother curve because we've got a deep slab. Again, the deeper something is, the smoother the profile, right? So if we have lots of jumps in our gravity survey, where's the profile? Where are the anomalies? Oh, it isn't the same. If you see, it's the same form, but it's much smoother, right? Right.
You said in that case they're the same.
Right.
Because you said when it's deeper, the anomaly should be.
No, I'm sorry. When it's deeper and it's truncated. Okay, so this is an example of a truncated slab. In that case, the depth does matter. Only if you have an infinite slab does the gravity anomaly not change the depth. Because when you calculate in an infinite slab, when you actually calculate the anomaly, you're integrating over all x for an infinite slab, okay? Which is to say that you're integrating for all angles. Well, you're integrating for all angles up here, you're integrating for all angles or all x down there, so it's not going to matter. Okay, so where might this curve be an example? Well, basically if we have mantle next to crust, okay, we're going to see a Bouguer anomaly like this. Notice what the free air anomaly does. Why is the free air anomaly like that? Again, we have water here, right, and then we have continent here. Well, what we're doing is we're basically pulling up the slab right here relative to here. So we've got a contrast in slab properties, just like we had in the fact that if we had a valley there, in this case it's an infinite piece of crust. So here's another example. This is called a Batman anomaly if it's just a free air anomaly. The Bouguer anomaly obviously just looks at the density contrasts. Which one is correct in this case? Is it the free air or the Bouguer? Anybody? Remember, in this case, if the continent is limited in dimension, neither is absolutely correct. Neither anomaly is absolutely correct. The Bouguer is probably more correct than the free air. Okay, so these are some examples. Use this as a reference graph. You can actually very simply in MATLAB program each of these formulas in and measure the gravity anomaly associated with them. And the applets and the code in Berger basically do that. The important thing on this side is a depth rule. Okay, so based on these equations, we have approximate rules on the relationship between these features over here and their depth. And that may be very important for drilling, or something like that. Okay, are there any questions about this part of the lecture? And I'm probably sure there will be. So again, what we've talked about is that we can represent, this is the formula that you really need to know, okay? You need to know how to calculate the response of a varied sphere. Right? Because why? Why do we need to know the response of the varied sphere? Or what are we doing when we calculate any gravity anomaly? Pardon? No, not really. So why is the buried sphere roughly the building block of calculating any other shape? Yeah?
Because if you look over a large area, you have a bunch of spheres, you kind of build out a whole topographic pattern.
Absolutely. Say that louder so everybody can hear it.
So if you figure out how all these spheres are affecting where you're measuring, you can kind of put them all together and build out a big
You
map.
put them all together. So what does that mean you do to the sphere? Well, it depends on your geology, but you want to make the spheres as small as possible, right? So R is going to go to some very, very small value. You don't care really what R is, right? Because you're not measuring, trying to characterize one sphere, you're trying to characterize the summation of all those spheres. So you're basically pixelating, if you want, just like you would in a digital image, you're pixelating a density model. Okay? And then you're simply using a formula You're using a buried sphere formula and adding up the response of all those pixelated positions. So let's think about that as a general process. So what we're going to do is we're going to